Remember the sort of goal here where we stopped off last time is this idea that we have this radical halogenation reaction, right? Where we're reacting an alkane with either chlorine or you can do it with bromine, okay, one of the halogens, okay, and this will produce an alkyl halide is what we called these. Right, where now you have an alkane that has a halogen on them. But so for example, if we take propane here, we perform this reaction, we could get two possible products depending on which chlorine, which carbon the chlorine gets stuck onto, right? And so we're gonna be working today to figure out which one of these two possible products is gonna be the major product of this reaction. So step one was learning about the stability of alkyl radicals. And we said that the most stable radical intermediates are on tertiary carbons, followed by secondary carbons, and then the least stable are going to be primary carbons. Okay, so given an alkane, we should be able to draw what the most stable radical intermediate is. Again, you're going to put that radical on the more highly substituted carbon, with the exception of what's missing from this list. The quaternary, right? Because they don't have any hydrogens that can be pulled off in this reaction. So for example, this one here, this purple carbon, even though it's more highly substituted than all the other ones, it's a quaternary carbon, there's no hydrogen, so it can't be the radical intermediate. Okay. So we're going to consider that when we figure out what our products are. And in fact, we can sort of put these numbers on just how stable a primary is versus a secondary versus a tertiary. So relative stability. Okay. So first of all, this is not a set of numbers that you'd have to have memorized. This is something that's going to be given to you on a quiz or an exam or whatever. You just got to make sure that you know how to use it. Okay. If you do have a calculator, that would be helpful. We're not going to do anything crazy, but we will be doing a little math with these numbers. Okay. So what this is saying is that if you're going to use chlorine in this reaction, relative to that primary alkyl radical, a secondary is about 4 times or 3.9 times more stable, and a tertiary is 5.2 times more stable. Notice that when you use bromine, those numbers are greatly increased, right? So for bromine, the secondary radical is 82 times more stable, and that tertiary radical is 1640 times more stable, okay? So we say that bromine is more selective, and we'll prove this using these numbers. Meaning that it will always goes on the more substituted carbon. So for example, if we take that same propane and we react it with bromine in this radical halogenation reaction, right, where we're going to use light. Since bromine is more selective, it's going to go on the more highly substituted carbon. So out of my two products here, I can determine that this is going to be the major product. All right. For chlorine, we're going to have to do some math in order to figure it out. Again, we kind of have those same two products. But in order to figure out which one is our major product, we're going to have to use these numbers here in order to figure it out, okay? Because while it's true, so if we zoom in here on our reactant, while it's true that these two primary carbons, all right, these are primary, are going to form less stable radical intermediates than this secondary carbon. That is true. How many hydrogens are there on that secondary carbon? There's 2. Right? Either one would have an equal chance of being removed in this reaction. But then how many hydrogens are there on, for example, this primary carbon? 3. And what about this primary carbon?
3.
Also 3. And so to some extent, it's a numbers game, right? There are more hydrogens on those primary carbons that, if removed, would lead to this product over here. Okay, so we have to take into account both of those factors. Both the fact that this is more stable, but there are just, in terms of the sheer numbers game, there are more hydrogens that would lead to this particular product on the substitution on the primary carbon. Okay, so that's what we're going to use this table for here. Okay, so what we're going to do for each of them is it's going to be the number of hydrogens times that reactivity factor over the sum of all the different carbons, number of hydrogens times their reactivity factor. Okay, so for we'll sort of keep these color-coded here. If I was going to do it on my blue carbon, I would do the number of hydrogens on that blue carbon, so in this case 2, times that reactivity factor for a secondary carbon, which is 3.9. But then I need to sum it up for all of these carbons, right? So not only am I going to account for that secondary carbon, but also those 6 primary carbons, right? And the reactivity factor for a primary carbon is 1. Okay, and so what I see is that this gives me a value of 0.57. If I were to do the same thing for the orange carbon, in this case, since there's only 2, I could just subtract 1 from that 57, but just to kind of do it the long way here. I'm going to use that 6 times 1 value and then divide it by that total, the 2 times 3.9 plus 6 times 1, and I should just get the reverse. .43. All right, and so what we just calculated is actually not just even what the major product is, but the fraction of each of these products that we would expect. We would expect a fraction of 0.57, or in other words, 57% would have the chlorine added to the blue carbon, whereas 43% would have it added to one of those orange carbons. All right, so indeed, my secondary carbon is going to be my major product. okay? But you see that we have to do the math because there's still quite an appreciable amount of that primary product in there as well, right? And so it's not a given that the chlorine is going to go on the more highly substituted carbon all the time. Let's take these numbers again and do another example. All right, and actually we'll practice what is the 3 things you should be able to do for this molecule with me. We're going to use 2-methylpropane. All right, the first thing that you should be able to do is draw me the most stable radical intermediate. And after that, I want you to draw me all possible products. All right, so that most stable intermediate, that radical, that dot, is going to go on the more substituted carbon, which is in this case that tertiary carbon in the middle. All right, and then how do I draw all possible products? You're going to just stick a chlorine on all the carbons that can possibly react, right? Which is any one of them that isn't a quaternary carbon. As long as it's not a quaternary carbon, it could possibly be reactive. So I can stick it on this middle one here. All right, I could also stick it on the top one, this side, and the other side. Okay, but importantly, I drew a few of the same structures multiple times, right? How many actual different products are there here? 2. There's only 2 of them, right? Because these are all the same thing, right? If you pick that up and rotate it, what would it be? What's a third of 360? 60? Yeah, sure, no. 120, there it is. If you pick it up and rotate it 120 degrees, I would get this structure. If I picked it up and rotated it 120 degrees again, I would get this structure, right? So they're just sort of drawn differently. They're rotational. If you rotate it, it's the exact same molecule. So there's actually only 2 products here. One where it goes on that middle carbon, and then one where it goes on one of those primary carbons. Okay? So then again, we're going to figure out, using our little reactivity chart here, make some room, we're going to figure out which one of these is our major product. Again, we said that it could either go here or here, and these three we're going to lump into the same category, right? Because if either one of them had the chlorine on it, we would get this same product. All right? So everybody take a second. See if you can't set this up mathematically to figure out which one of these is going to be our major product, and then we'll do it together. All right, but again, you're going to take the number of hydrogens times that reactivity factor, and then divide it by the sum of all hydrogens times their reactivity factor in this molecule. Two of them, one for our blue carbon, and then one for the orange carbon. Probably do these on top of one another. All right, our blue carbon produce that product there. I don't know why I drew that bond so small. And our orange carbon would give us this product here. So how many hydrogens are there on that blue carbon? One. All right, here there's just one. It's already got 3 bonds, so the only missing hydrogen is just one of them. Right, so 1 times, and then what reactivity factor would I use? It's a tertiary carbon, right? We're talking about a reaction with chlorine on a tertiary carbon, so that reactivity factor would be the 5.2. Okay, and we need to divide it by the sum, but let's just look at this orange carbon real quick. Right? We're going to lump all those orange carbons into the same group because they would all give us the same product, right? So then each one of them is going to have how many hydrogens on there? 3 in each one of these. But I need to put them all into one group. So how many hydrogens are in that orange group total? 9. Right, so for this one, it'd be these 9 times that reactivity factor. And what reactivity factor would I use? 1, because now this is a group of primary carbons. Right, so 9 times 1. So then when I sum it up, it's going to be the 1 and the 5.2 plus the 9 hydrogens in group 1. 1 times 5.2 plus the 9.1. All right, and so if I do the math, I would see that this comes out to 0.37, and this comes out to 0.63, right? Meaning that 37%, about a third of it, would be on that more highly substituted carbon, but actually the major product would have substitution on that primary carbon. Okay, and again, it's just a numbers game. There are just so many more primary hydrogens that could react that even though each one individually is less reactive, because there's so many more of them, the probability that that would be your major product is greater, right? So again, about 2/3 of your product would actually have the chlorine on that more highly substituted carbon. All right, let's do one more. Yeah, in this case, the more highly substituted carbon is actually the minor product. Okay? But again, that's because we got a numbers game going on where there's only one hydrogen that would react to produce this carbon, but there's 9 that would react to produce this product. Right? And so even though each one of those 9 hydrogens individually is less reactive than this one, together the probability would be greater because you got just 9 of them, right? 9 versus 1. So that, at that point, the numbers kind of win out. All right, so let's do one more. I'm going to do pentane. All right, so again, draw me that most stable intermediate. And then draw me all the possible products. All right, how many different products do we get?
2.
So there are 2, we got more than that though. 3, okay? So I can put it on the end. I can put it on one of these 2 here, right? So both of these N carbons would give me the same product. I could put it on these ones here. Okay. But if I put it on this very central carbon, this one in the middle here, even though it's also a secondary carbon, I would get a different product than if I put it on one of those blue carbons. Right? So we're going to now have to lump these into 3 different groups instead of just 2, because I have these 3 different possible products. Right? We're going to call this one the orange group, if it goes on that end. If it goes on either of these orange carbons here, I would get this same product. We got the blue group, because if it goes on either of these 2 carbons, I get this same product. And then we got the purple group, because if it goes on this middle carbon, I have this 3rd product here. Right? So these are our 3 different possibilities. Which means that now when I do my calculation to figure out which one is my major product, I'm going to have to do 3, 1 for the orange group, 1 for the blue group, and 1 for the purple group. right, we'll call the orange group Group A, the blue Group B, and the purple Group C. My bad if anybody's colorblind for using colored groups here, but cool. So, see if you can't set this up. Again, you're gonna have to do 3 different calculations. Previously, we only had 2 groups, so we did 2. Now you're gonna have to do 3. Again, the sort of frame of that formula that you're gonna be using is number of hydrogens times the reactivity factor divided by the sum of all the different groups, number of hydrogens times reactivity factor. All right, so take a minute and see if you can't set this up. All right, so let's do it here. So, how many hydrogens are in group A, our orange group? 6, right? I got 3 on that one orange carbon, 3 on the other one. So that'd be 6. And the reactivity factor for the orange group? 1, right? Because it's a primary carbon, okay? I'm going to go across and figure out what the numerator is for each one, because that's what we're going to be summing up at the end, all right? So then how many hydrogens are there in group B, in the blue group? 4. And what's the reactivity for group B? 3.9. What about group C? How many carbons? Nope, not carbons. How many hydrogens?
1.
Not 1, 2, right? Because it's still a secondary carbon. and then the reactivity factor is 3.9. Both the group B and C are secondary carbons, but we got to treat them differently because they would each give us a different product. All right, so then I'm just going to divide each of these by that sum, 6.1 plus 4 times 3.9 plus 2 times 3.9. Right, the denominator will be the same for all of these. All right, and what I would find is that this, for group A, it's going to be 0.20. For group B, it's 0.53. And for group C, it's 0.27. All right, so then which one is my major product? B. 53% will be B. 27% will be C, and 20% will be A, right? That's what those calculations are telling us. All right, we're actually going to do one more here because I want to make sure y'all can do this on your own. All right, it's one thing to be able to follow along with it when I'm walking you through it, and it's another beast to be able to sort of do it from scratch here. All right, we're going to do butane. Draw me my possible products and determine which one is the major product using those reactivity factors.
So why did the last problem not have the third group, why wasn't it not tertiary?
Because, right, so first of all, primary, secondary, tertiary is really about how many neighbors that carbon has. And so both of these are actually secondary carbons because they both have just 2 carbon neighbors and 2 hydrogens, right? The reason that we're putting them into different groups is not because they're different degrees of substitution, but because they would lead to different products, right? So despite the fact that they're both secondary carbons, the purple one would lead to this product here where the chlorine's on that 3rd carbon. And if you put it on either one of those blue carbons, you would get this product here, right? So we had to put them in 2 different groups, not because they were different degrees of substitution, but because they would lead to different products. Oh, that's not what I meant to do. so we got these two different products that we could possibly get. Again, we're going to call them group A and B here. Okay, if I put a chlorine on either one of these terminal carbons, that would lead to this product in group A. If I put it on either one of these carbons, that would give me that same product, which we're going to call B. Okay, again, we're trying to figure out which one our major product is. How many hydrogens are in group A? Yeah, how many hydrogens are on these orange carbons? 6. The reactivity factor of group A? 1. What about how many hydrogens are in group B? 4. And then the reactivity would be that 3.9 because it's a secondary. All right, so then sum that all up. Okay, and I would get that 0.27 or 0.28, I guess, rounding it, and 0.72, right? So 28% would be product A. My major product, 72%, would be product B. What's up?
So something I noticed in all our examples, it has to add up to 100%.
It's definitely going to add up to 100%. Yep, absolutely.
Over, under, obviously wrong.
Correct. Yeah. If you get any if this number is anything bigger than 1, something went wrong when you punched it. And actually, that's a good point. The number one thing that probably would go wrong is order of operations. You will need to make sure to put that bottom, that divisor in parentheses. Otherwise, it's going to jack up your order of operations, right? You need to combine those before you do that division step. So if you're getting a big number, that is most likely why, right? You need to keep all this stuff down here on the bottom of that in the denominator there. So you're going to put it in parentheses when you put it into your calculator. Okay, and I just want to go quick, but let's just go back to this one here. This was our surprising one where we found that our major product was actually that primary carbon. If we did this exact same thing, but instead used bromine, and you guys can convince yourself of this by doing the math, I'm just going to sort of state real quick what the results would be. Remember we said that bromine was more selective, and you can tell by the math. Let me just get rid of this so it's not confusing. Tell by the math that's because these numbers are so much larger than they are for chlorine. And we said that bromine was more selective, meaning the major product was always on that more substituted carbon. And you could do the math using this column of numbers here, and you would indeed find that 99% of that product would be on that more substituted carbon, and only 1% would be on that primary carbon, despite the numbers game of having 9 times more primary carbons than we do tertiary carbons. All right, so again, you can use these numbers to prove it, but what you're going to see is that the more highly substituted carbon is always more favored with bromine. All right, the last thing we want to do real quick, because I want to make sure you guys have this for your homework. We're going to learn how to name these products now. Right, we got all these different alkyl halides. We're going to learn how to name them. And it's actually very, very simple. The only thing we need to do is learn how to name these substituents. Right? So if it was an alkane substituent, we said that it ended in YL, like methyl or ethyl. Fluorine is a fluoro group. Chlorine is a chloro group. Bromine is a bromo group, and iodine is an iodo group. So I'll move these on to another page here. So then how do I use this? Let's say that we have something like our major product from that first reaction with pentane was this one here. So how do I go about naming this molecule? I'm going to do the same procedure as before, right? What was step 1? The parent chain, right? Find that parent chain, the longest continuous set of carbons. 1, 2, 3, 4, 5. So our parent chain is a pentane. The next step was to name our substituents. And again, before we saw methyl groups, ethyl groups, but now my substituent is a chloro group. All right, just like before, we got to indicate the position of that chloro group. So I'm going to number my parent chain, and we can always number it in either direction. In this case, which one of these numbering schemes am I going to pick? The red numbering scheme or the purple numbering scheme? Purple, because that's going to put that chloro group on the smallest number. And so this would be a 2-chloropentane. All one word.
We don't put methyl.
There's no, it's not a methyl group now, it's a chloro group, right? Because it's a chlorine. If it was a CH3, it'd be a methyl, but there's no carbon. It's instead a halogen. So take a second and name this one for me. So my parent chain, 1, 2, 3, 4, 5, 6 carbons. Now my substituent is a bromo group. Say that again?
Hexane?
Yes, exactly. So our parent chain is a hexane because of those 6 carbons. I got my bromo group. Exactly. And it's located on carbon 1, 2, 3. Because if I went the other way, it would be 4. So I'm going to pick the lowest number. So 3 bromohexane. All right, and just to do this one real quick, same sort of procedure. This now has a mix of an alkyl substituent and a halogen substituent. That's perfectly fine, right? Our rules don't change. Find the parent chain, 1, 2, 3, 4, 5, 6, 7. So my parent chain is a heptane. I'm going to name my substituents. This is that halogen. It's a fluoro group. Okay, this is a 2-carbon alkyl group, which we would call, if it's 2 carbons, an ethyl group. I'm going to number my parent chain. My red, it would be 4, 5, compared to my purple is 3, 4. So which one's better? The 3, 4, the purple. And then now, remember, what do we do when we have multiple substituents? How do we construct the name? Alphabetical order, right? So same rule applies. Nothing crazy. All we've done is introduce now a new type of substituent are halogen substituents. Everything else is the same. So A, B, C, D, E, F. Okay, so ethyl comes first. So 3-ethyl 4-fluoroheptane. All one word, run together. All right, so again, we got these new substituents are halogens, the fluoro group, the chloro group, the bromo group, and the iodo group.